This video is a demonstration of the FIFO soft IP block on the Gowin FPGA on a Tang Nano 9K FPGA development board. FIFOs, or first-in, first-out buffers, are commonly used in logic design when crossing clock domains. We'll talk briefly about what those are and then dive into an example. I'll show how to instantiate a FIFO using the Gowin IDE, and we'll see it work getting data from one clock domain to another. A clock domain is a set of logic driven by one clock. Sometimes designs must use multiple clock domains because part of the logic must run with a faster clock than is possible for another part of the logic. For clock domains to interact, data must move from one to the other. Doing this is not trivial because bad things can happen. Data from a faster domain might be lost because it changes too fast for logic in the slower domain to sample it. Our example will have this issue. Another problem is that clock phases are not necessarily aligned, so a signal might be in the middle of transitioning from one value to another when logic in the other domain tries to sample it. This is a setup time violation. It might lead to metastability. There are many sources of information on this. See below for a link. Correct methods for transferring data from one clock domain to another include dual flop synchronizers, see that link below, and FIFOs. We'll focus on FIFOs. Designing them is tricky, so manufacturers like Gowin provide them as soft IP blocks. As I will show, you can add FIFOs to your project in the Gowin IDE using the IP core generation tool. You can create many variations of them. This diagram shows a typical case. There is a side to which data is written and another side of the FIFO from which data is read. They can be in different clock domains, so the FIFO interface provides two clock inputs. When creating the FIFO, you can say how wide the data will be and also how many data instances can fit into the FIFO before it is full. This is called the FIFO depth. To write to the FIFO, first check the full signal to ensure there is room and be sure the data to write is stable, and then assert the write enable signal. The data will enter the FIFO on the next write clock cycle. To read from the FIFO, check that the empty signal is false. If it is true, there is nothing to read. Assert the read enable signal, and then data will appear on the output lines on the subsequent read clock cycle. The Gowin FIFO User Guide document IPUG 105 provides timing diagrams and more information. Here's the Gowin IDE. We can see what version we have here. So I'm using version 1.9.9.03 on Windows. And this project file has two top-level files, top bad and top good. And only one of them can be enabled at a time. So right now we have bad enabled, and so let's take a look at it. And so this module is connected to the LEDs of the board and is using a 27 megahertz input clock. And the goal is to just make those LEDs blink in a counting pattern. And so let's see how this is trying to do it. So here in the fast clock domain, we have a clock that's running at about 19.3 megahertz. And we simply have a 30-bit counter that's counting continuously. That's all that's happening in the fast clock domain. Now the trouble starts in the slow clock domain. So here's a clock that's running at 4.5 megahertz. And by the way, both of these clocks are produced by Gowin PLL instances. But anyway, here in the slow clock domain, what it's doing is that it's looking to see if the lower 24 bits of the counter are all zeros. And whenever that's true, it's copying the value of the upper 6 bits of the counter into the LEDs, and that would make the LEDs count. But I think you can see that there's problems with this. The counting is happening at more than 4 times the speed that the slow clock domain is running at. So it's quite possible that the counter will be 0, and this test will never see it, because it'll never sample the LEDs being all zeros. It's also possible, since we don't know the phase relationship of the clocks, that we'll have intermediate states, potential problems with metastability. We could even end up in a state where some of the LED values are correct and others aren't. There's really no way to know. But I think the most obvious thing is that we're likely to miss counts because, there's never a sampling during the time when counter is 0. So let's run it and take a look at that. So we can do a quick build. This is a very small project, so it's fast. And then we'll load it. And now let's cut to the board and see what it's doing. So here we go. It's showing 1, and it just counted to 5. and now it's going from 5 to 9. So just as we expected, it's not counting properly. There's something badly wrong with this implementation. So now we're back at the Verilog. Let's close the bad file, disable the bad file, and enable the good file. So now opening this, we have an implementation that will work. And of course, the difference is that this one involves a FIFO. So it's instantiated here, and I'll show you how that's done in a minute. But now we can look at the connectivity. So the data that goes into the FIFO is the upper 6 bits of the counter. That's connected to data. That's the input data for the right side. Here's the reset. The write clock is the high-speed clock. The read clock is the slow domain clock. And then we have signals write enable and read enable that we'll see in a second. And the output of the FIFO when read goes to FIFO out. And then here's our empty and full signals. So now, if we go back up to the fast clock domain, it's a little bit different. We still have our counter counting, but now the fast domain is doing the checking. So when the lower 24 bits are all zeros and the FIFO is not full, what the fast domain does is simply toggle the write enable. So that will cause the value of the upper 6 bits to be written into the FIFO whenever the lower 24 bits are all zeros. What actually happens is this. During the clock cycle, when the lower 24 bits are 0, we set WREN to true. This takes effect during the next fast clock cycle, when the lower 24 bits of the counter are 1. It's during this cycle that the FIFO accepts the upper 6 bits of the counter, but this is okay because they will not have changed. And now on the read side, here in the slow clock domain, so what that's doing is it's checking to see if the FIFO is empty, and if it's not, all it has to do is to set read enable to 1, and then it'll be toggled to off on the next clock cycle. FIFO out changes during the cycle in which the read enable is high. LED reg captures that, so we can see the new value of the upper 6 bits of the counter on the LEDs. So you can see this actually happens on every clock, so because we can just wait. FIFO out stays stable until a read occurs, and then it changes in one clock cycle, and LED's register sees the updated value. So that's how this works. It's all pretty simple, and maybe we should see this guy run. So once again, we can do a build because it's quick, and we'll load that. And we can cut to what the board is doing. 1, 2, 3, 4, 5. It's counting properly this time. The FIFO works. Actually, it's possible to simplify this program. You could delete this entire always block and connect the LEDs to the output of the FIFO directly and tie the read enable signal to high. And that would cause the FIFO to basically read whenever there's data to read. And the only downside of this is when the lower 24 bits of the counter are 0, at the time you reach that point, you'd actually be seeing the previous value of the upper 6 bits. But if you just want to see it count, it would work fine. The reason I mention this is because you do have to pay careful attention to exactly when things go into and out of the FIFO. So it pays to look at the timing diagram in the documentation. Let me show you how to instantiate FIFO. So that's done like all of the hard and soft IP using the IP core generator tool. So you open that and then go down to, I think it's memory control and FIFO. And so just double click on this and it brings up lots of choices. And so for us, what do we need to change? Well, the width is 6 bits. So I changed that to 6. The depth we can leave alone. Our application doesn't need any significant depth of the FIFO, so the minimum is fine. I like to use the SSRAM just because entire BSRAM blocks get used, so it's wasteful. In some of my other projects, I need to conserve BSRAMs. And then down here, you can select a reset and make it so that there's only one reset signal. And I had no need of these output signals almost full and almost ready, so I disabled those. And that's fine. So then you say OK, and I've already got one, so it says, do I want to override it? Yes, it generates it, adds it to the current project. And then, like always with the IP generation tool, it creates this thing that you can paste into your program, and then you edit it with your actual signals. But of course, we've already done that, so we can just get rid of all of that. We've seen a simple example of using a Gowin FIFO to move data from one clock domain to another. I'll put the project for the Tang Nano 9K onto GitHub. It would be easy to adapt it for the Tang Nano 20K. I plan to use these FIFOs in a future project in which I need to run a peripheral with a faster clock than the Pico RV32 RISC-V core can support. I'll end this video here. Thanks for watching.